Okay. So what is the bipartite matching problem? Well, again, of course, as the name suggests, you have a bipartite graph. Suppose you have this graph. Yeah. And you have edges. I don't know, something like that. Okay. So input is a bipartite graph, let's say. G equal to V. Okay. So let me call this X, Y, and E. Okay. So this side is X, this side is Y, and E is the set of edges. Yeah. What is the matching? Best shown by a picture. So that is a matching. Yeah. Let me give some names. So X1, X2, 3, 4, Y1, Y2, Y3, Y4. Okay. So these green edges form a matching. And what is so special about the green edges? Well, these green edges, they do not share any common vertices. Yeah. So if you remember, we are talking about undirected graphs now. So this is an undirected bipartite graph. I mean, of course, bipartite graphs are by definition undirected, but yeah. So if I look at these green edges, then they form a matching because there are no common endpoints for these green edges. Yeah. Good. Now, what is the goal? Well, the goal is to find such a set of edges in the bipartite graph. Yeah. Why is this problem important? Tons of applications. So you can think about some resource allocation kind of thing. So let's say the left-hand side are jobs which can be performed by some processors on the right-hand side. So you want to, assign one job to one processor. And if you want to think of, more practical applications, you can read up on the internet. There are tons of applications of the matching problem. And okay, great. But let's now come to the technical part of matching. Okay, so what is a trivial matching? So if I give you a bipartite graph, what is a trivial matching in that graph? In fact, for any graph, the matching problem is defined for any graph. It has nothing to do with bipartiteness of the graph as such. We are talking about bipartite graphs because we will look at it from a max flow point of view. Okay. So what is a trivial matching in a bipartite graph or in any graph? Right. Exactly. So the null set, don't pick any edge. That is clearly a matching. So of course, now we are interested in a special matching, which is to find the matching with max cardinality. Okay. So clearly now, there is one more edge that I can add to this matching, which is this edge. This edge, right? So I can add x4, y2 to my matching. Is this the maximum matching in this graph? Probably, right? Actually, no. This is okay. Good. Is this the maximum matching in this graph? No. Good. So which is the maximum matching in this graph? X3, Y3 is already part of the matching. Okay. Good. So let's see another larger matching, which is the following. So what I can do is I can instead take the red edge here. I can take the red edge here. Yeah. And the rest two I keep the same. So this is another edge. This is another edge. ठीक है? So the red edges form a matching which is of size 4 vis-a-vis the green matching which was of size only 3. Yeah. But remember, if you look at the matching which is of size 3, you could not have added another edge to that matching. Okay? This is a bit important to realize. So if you look at the matching that I previously had drawn, which is the edge x1, y1, x3, y3, and x4, y2, the green edges, then you could not have extended this matching by adding another edge to the set. Yeah, whichever edge you tried to add, you will end up violating the condition of a matching, right? So those are known as maximal matchings in your graph. Yeah. So what is a maximal matching? It's a matching which you cannot improve upon by adding one more edge to your matching. Yeah. So let me actually say this. So maximal matching which cannot be extended. Cannot be extended. Yeah. So the green edges form the maximal matching. Please remember, maximal matching is not a maximum matching, clearly, as in this example. Yeah. So maybe you could have done things differently, which would have given you a larger matching. Okay. Now, I hope that you are already convinced about the non-triviality of this problem. Yeah. And let me tell you that all obvious algorithms will fail for this problem. Okay. By the way, what is an obvious algorithm for this problem? If you did not know anything about, let's say, maximum flows and everything, and you saw this problem, then what is the first attempt that you are going to try or you are going to make? Greedy. Good. There is a greedy answer. Try all subsets of edges. Very good. That's an even better answer. Unfortunately, that's an exponential time algorithm. So yeah, if you try all possible subsets of edges, you will end up finding the maximum matching. But that's like not something which we want, right? We want a polynomial time algorithm. Greedy. So can you spell out, whoever answered greedy, can you spell out what a greedy algorithm could be in this case? So attempt 1 is greedy. Attempt 1. So can anyone tell me like what could be a natural greedy algorithm to solve this problem? Take the lowest degree vertices. Yeah, that's a good point. Okay, so it turns out that even if you do something slightly more dumb, which is just take any edge that you can take. Okay, so the point is what you said is also a greedy algorithm, but uh, all I'm saying is there are examples where if you just check all the edges with intersecting edges. Exactly. So basically you look at a vertex. Okay, Oshin, just hold on. I mean, I'm just, yeah, we'll come to that. Right. So yeah, a natural greedy algorithm is to essentially find a maximal matching. Yeah, right. So you pick the first edge, and then you check whether, and then you add this to your matching. Then you try to add the next edge. If it is in your matching, then you add it. If it intersects with anything in your matching, you cannot add. If it's allowed, then you just keep adding. ठीक है? ऐसे आप चलते चले जाइए. Yeah, you take the edges in any order you want. Attempt 1 is, I will just leave it at find a maximal matching. Okay, so that's yeah, and this is what I would try if I saw this problem for the first time. Yeah, there is no reason to believe that this can be solved using max flow, or I mean, at least it's not immediate. Okay, so I'll give you a fact, and probably I will give this as an exercise. Greedy algorithm can be a factor 2 less than optimal. Okay, so basically you need to find an example where this greedy algorithm will end up having a size which is half what an optimal matching can do. Yeah, so this would be some problem. Okay, good. So that's not what we are going to talk about anymore. So attempt 2 is I want to apply the maximum flow algorithm. Okay. So now there are a few things that we need to address. So what are the obvious differences? How on earth am I going to apply maximum flow algorithm on this graph? So there are a few problems here. First of all, so we do not have less than or exactly half. It's actually slightly more than half. Okay. Yeah, so the answer is if I give you any, let's say n, then you can construct an example where the matching size is something like n, but the maximal matching will only have n half or something like that. Yeah, so yeah, just figure out the rest. Okay, so how are we going to apply max flow to solve this problem, right? So there are kind of a few bottlenecks. The first bottleneck is this is not a directed graph. Remember, when we talked about flow problems, we have always talked about directed graphs. So we need to figure out a way to somehow give directions to these edges. Secondly, there are no source and sinks. And third, of course, is there are no capacities associated, right? Okay. So yeah, so I think there are a couple of ideas already floating around. So what some people are suggesting is the following, that so suppose this is your graph. Okay. Now I construct a flow network out of this graph. Yeah. So that it solves my matching problem. So the flow network is as follows. I add an artificial source on this side. I add an artificial sink to this side. Right. Okay. Of course, these are the edges that are given to me. Yeah. But I will add a few additional edges now. Yeah, what are the additional edges? Well, as Sayam is saying, and probably someone else has also said before, essentially, okay, let me just show the new edges in green. So I will add a directed edge to every vertex on this side to T, and every vertex from that side, from S to this side and from this side to T. Yeah, this is my set X, this is my set Y. Okay, so that solves my source sink issue. Okay, and okay, let me also give some directions to these edges. I just choose this direction, right? You could have also done the other way around. Yeah, so make whatever. Yeah. Okay, how about the capacities? What should be the capacities on the edges? 1. Okay, so you want to make all the capacities to be 1? That in fact works. Okay, so yeah, what she's suggesting is I will make the capacity of each of these edges to be 1. This I definitely need. Yeah, and you will see why this is important. For the other edges, actually you are free to choose any capacity you want. Okay, and there is a reason that I will set this to be plus infinity. Okay, so plus infinity means a very large number essentially. Okay, there is no, so right now there is no reason that I should have done like this. As she's saying, if you just set a capacity of 1 on these edges, this will also solve your maximum matching problem. But I will, in a later part of the lecture, I will require this fact that these capacities are plus infinity. Yeah. So that is going to be your flow network. And I claim that if you solve your maximum flow problem on this network, then it will help you find a maximum matching. Okay. So think about this for 5 minutes. You will surely get the answer, and we'll talk about this next time. Any questions about today's anything that we talked about? Yeah, I said that one will work, but I need infinity for a different reason. So for solving the matching problem, setting a capacity of 1 will also work. That's correct. Any questions? And what I want to find is a set of edges so that their endpoints do not intersect. Okay, so I will try to pick a subset of edges in the graph such that if I look at any two edges, then they do not share any common endpoint. Yeah, that's a matching. And as we saw that there could be several matchings in a bipartite graph, including the trivial matching, which is the null set of edges. So the idea would be to find a matching which has the maximum possible cardinality or maximum possible size. Okay, so that's the problem. And we also briefly mentioned that an obvious algorithm for this problem would be to go greedy. Yeah, so you start with any edge you want, and then you just keep taking edges as long as you can, essentially. Yeah, so you take an edge if it does not intersect with any edge that you have selected so far, and you carry this on as long as you can. This will give you a matching for sure at the end, but yeah, so this is not an optimal algorithm. So there are examples where this could be a factor 2 away from the optimal. Okay, so which is why we need to find a different algorithm for this problem. And what we'll do is simply reduce this problem to a max flow setting. Okay, and the reduction here is pretty straightforward. Yeah, so basically, again, remember this was our bipartite graph. So now I give some directions to the edges. So let's say, yeah, I give some directions arbitrarily. Let's say all the edges are going from X to Y. And then I also added a source vertex and a sink vertex. Yeah, and everything that is on the X side, I connected to S, and everything that is on the Y side, I introduced an edge from those vertices to the sink T. Okay, so that is how we reduce the problem. Now let's quickly see why solving an ST max flow gives an answer for the maximum matching problem. Well, it's pretty straightforward to see, but let me state the theorem nonetheless. So theorem, so matching of size say k is equivalent to flow of value k in G prime. Okay, G. Yeah, so G prime is this network that we have created, and let's say G is the original graph. So we claim that, you know, any matching of size k has a one-to-one correspondence with a flow in this graph that is of value k. Yeah, and if we can prove this theorem, then we are done essentially, right? Because then the maximum value of the left-hand side will be exactly equal to the maximum value of the right-hand side. Right? So let's quickly see why this theorem is true. I'm not going to do a formal proof. I think the proof is it just writes itself. So let's try to prove one direction. So suppose I give you a matching of size k, right? So suppose, let's take an example matching. So suppose I give you, I don't know, this matching maybe. So let's say I give you this edge, I give you this edge, and I give you this edge. Okay, so this is a matching in this graph, which is of size 3. So I don't know, maybe today there is a slight lag between what I'm writing and what you are seeing, but I will try to make the presentation robust to that problem. Okay, so suppose these blue edges are my matching. Now, one can easily construct a flow of value 3 given these matchings, right? So basically, you look at the vertex on the x side, which is part of the matching. You just take the corresponding edge from S, right? So you basically take this edge. And similarly, you take the corresponding edge that connects the other side of this edge, which is in the matching, to T, right? So that essentially gives you one path in this directed graph, which goes from S to T. And it's pretty straightforward that if you go on like this, then you will have k different paths. So if k is the size of your matching, you will end up having k paths. Moreover, these paths will be edge disjoint, right? Because these blue edges which we started off with, they are part of a matching, so they are all disjoint. And if I extend that construction to this flow setting, then those paths will surely be disjoint. And so if you have k edge disjoint paths, then you can also have a flow of value k. Yeah. So any matching of size k directly translates to a flow of value k in this network. How about the other direction? Well, suppose you have a flow value of k, right, which is going between S and T. Now, we know that by the integrality of flow, every edge will have a flow value which is an integer. Yeah. So every flow will be of value at least 1. And if every edge will have a flow value of at least 1, then I'm essentially done, right? Because then I can say that, well, I just look at, I can again sort of apply this decomposition into paths, and then I can just pick the edges which are part of, so the pick the edges between X and Y, which are part of these paths. Yeah. So the only thing that one needs to make sure is that, that 2 units of flow, so essentially more than 1 unit of flow, is not coming into any of the vertices of X or Y. Yeah, that's the only thing we need to check. But clearly that cannot happen, because the incoming edge to any vertex in X, that has a capacity of 1. Similarly, an outgoing edge from anything out of Y, that has a capacity of 1. So there is no way that you can have 2 units of flow coming into either X or flowing out of Y. Yeah, which means that each of the vertices in this flow, they will have like 1 unit on them. Yeah. So that again gives you a matching of size k in this graph. Yeah. So so this is almost like the edge disjoint path theorem that we had proved, but slightly different. Okay. Any questions about this? So this just proves that if you apply this algorithm, then it straight away gives you maximum matching in your graph. Okay. So what is the runtime of this algorithm? So what is the runtime of this matching algorithm? Runtime of max flow based algorithm. Okay, can anyone tell me what is going to be the runtime? So remember, now we have to state the runtime in terms of the number of edges and vertices in the graph, because these capacities and all that we have introduced because we wanted to reduce it to max flow. Okay, so someone says that the answer would be order V times E, right? So let's see why that is the case. Well, if you want to think of the Ford-Fulkerson algorithm, then runtime of FF, what was that? Well, that was order E times U, or I think I used the word C. So what was C? C was the total capacity of edges in delta plus of S. right? So this was the runtime of the fourth Fulkerson algorithm. Now, if you look at this setting, then what is C here? Well, the total capacity that is going out of C is equal to the total number of vertices on each side. So you can simply replace C with n, with mod of V, yeah, or n if you want. So this is equal to order E times V. Okay. So this is not too bad. So this is like number of vertices times number of edges, which is okay, reasonable. Yeah. So so this is some fact. So there exist algorithms for maximum bipartite matching in order m square root n. Okay, so such algorithms do exist, but well, this does not really go via reduction to the flow problem, but it uses some ideas from flow literature. So it also has a notion of augmenting path and stuff like that. But yeah, this is an advanced material, so we will not be covering this algorithm. But yeah, you should know this fact that bipartite matching with max cardinality can be solved in time m square root n. Yeah, so m is, yeah, essentially this is E. Okay, so that's the story. Any questions so far? Okay, great. So today we would see some applications of a min cut. Okay. So far we have seen two applications of max flow. One is the edge disjoint path, another is bipartite matching. We'll be seeing a lot more applications in tutorials, exercises, and so on. So especially there are some interesting problems that, you know, so when you see those problems, you don't realize sometimes why this should be solvable using max flow, but it turns out that one can often do some nice reductions and apply the max flow algorithm almost as a black box. Yeah, so hopefully we'll see such examples over the next 2 weeks. Okay, but today we will see two applications of min cut. So the first application, again, it comes from matching. So we'll be talking about perfect matchings. Okay. So what is a perfect matching? Again, I'm talking about bipartite graphs. So the setting is exactly the same. So let me draw a picture. Okay. So this is again X, this is Y. Let's give some names again. X1, 2. Okay. So again, I have a bipartite graph and I want to find a, so what is a perfect matching? Well, a perfect matching is, okay, so assume here, so I'm assuming here that mod x equal to mod of y. Let's say this number is n. Yeah. So suppose that both the sides have same number of vertices. Now the question is, does there exist a matching of size n? Okay. So the question we ask is, does there exist a matching of size n, which essentially means that does there exist a matching that matches every vertex in the graph? So when I look at the edge set, then every vertex appears as an endpoint of at least some edge. Yeah, so that's a perfect matching. And this is also known as sometimes assignment problem. As I was saying last time, maybe that, maybe these are some jobs you need to assign to some machines to get processed. So you want to make sure that every job is assigned to some machine. Yeah. Okay. So the question we would address is, does a perfect matching exist in the graph? Okay. Note one thing, that if a perfect matching exists in your graph, then if you apply the above algorithm that we have described, then it will surely output this matching. Yeah, clearly, because this algorithm is computing the maximum matching, and a perfect matching is really the maximum matching in this graph. So if there exists one, then I will get one. But the question we're asking is, under what condition will a perfect matching exist in a graph? So let's look at this picture. Okay, does a perfect matching exist in this graph? Okay, good. So many people are saying no, 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 no. So good. So how are you so sure that there are no perfect matchings in this graph? Okay. Yeah. So if I just look at it immediately, it's not clear that a perfect matching will not exist, because there are yeah. So there are 5 vertices on the left side. There are 5 vertices on the right side. So at least if I look at it from that point of view, then a perfect matching can exist. There is no reason. I mean, there is no problem there. But the issue is the following, right? As some people have pointed out already, if I look at this set of vertices, so let's say I just look at this set of vertices, yeah, x1, x2, x3. So remember, what is the neighborhood of this set? What is the okay? I did not define neighborhood, but I think it's a self-explanatory definition. So essentially, what is the set such that this set of vertices x1, x2, x3 has an edge to that set of vertices on the right-hand side? Well, if you look at it, that set is y1, y2. Okay. So it turns out that we have a set of vertices S in this side, and this is the neighborhood set, such that the size of the set S is strictly bigger than its neighborhood set. And now this is a clear bottleneck, right? If I have 3 vertices, which are only neighbors to 2 vertices on the right hand side, then clearly I cannot match all of x1, x2, x3. You can at most match 2 out of x1, x2, x3, but clearly you cannot match all of them. Yeah. So this set, the existence of this set S in this graph is a bottleneck for the existence of a perfect matching. And immediately, if I can produce such a set, then I can claim that a perfect matching cannot exist in the graph. Okay. So if there exists a set S belongs to X such that mod of S is greater than mod of the neighborhood of S, then no perfect matching. Okay, everyone okay with this? But the question we ask now is a stronger one. What we ask is, are these sets the only bottleneck in the road towards finding a perfect matching. Okay, so I'm asking a stronger thing here that ठीक है, ये जो set है, if such a set exists, then there will not be a perfect matching. But suppose there does not exist such set, whose neighborhood has a smaller size than itself. Then can we guarantee that there will always exist a perfect matching? Okay, so the question I'm asking is, if for all s belongs to x, mod of s is less than or equal to mod of n of s, then does there exist a perfect matching? Yeah, everyone with me? Good. So yeah, some of you might be knowing about this. So the answer turns out to be yes. Yeah, and this is formalized by a very, very well-known theorem in graph theory and matching theory, which is known as the Hall's theorem. Okay, so the theorem, so this is Hall's theorem. Okay, so it essentially says that this is an if and only if condition. So for all s belongs to x, mod of s is less than or equal to mod of neighborhood of s is equivalent to existence of a perfect matching. Okay, everyone understands the statement of this theorem. So the point is, if you want to convince me that there does not exist a perfect matching, well, you just have to produce such a set. Yeah, and these sets are also known as Hall sets. So sets with mod s greater than mod of ns are called Hall sets. Okay, so now what we'll do is we will see how max flow equals min cut theorem essentially implies Hall's theorem. Okay, so when Hall proved this theorem, he did not have the tool of flows and cuts. Flows and cuts were discovered much later. So there is a different proof of this theorem. One side is pretty straightforward. So if there is a perfect matching, then clearly this statement has to hold, right? The other side is what is slightly tricky, that if this statement holds, if the left hand side holds, then how do you convince me that there is a perfect matching? That is a slightly tricky one, but we will see that this is like an almost immediate application of max flow equals to min cut. Yeah, so some of you might be aware of a different proof. You can use induction and stuff like that, but yeah, we will see a different proof of this theorem. Okay, so let's just do one side first. So maybe I do this side first. So if a perfect matching exists, then clearly for every s belongs to x, mod of s is less than or equal to mod of n of s. Yeah, so this is very straightforward. So you pick your favorite set s. Yeah, remember I have a perfect matching. If I have a perfect matching, that means that something like this exists. So if this is s, then this is neighborhood of s. So I know that the neighborhood of s contains at least as many vertices as s. Yeah, so yeah, by the existence of the perfect matching. So this side is very straightforward. What we'll do is the other side. Yeah, so suppose mod s is less than or equal to mod of s. Okay, now let's look at this picture again. Okay, actually let me draw this again. Yeah, I don't know, something like this. Yeah, doesn't matter. Okay, so that's your bipartite graph. So the way I will prove it, I will construct again the flow network that I had shown you above. Yeah, so I will add a source and directions to these edges, and I will add a sink. Okay. So these will have capacity of 1, and these will have capacity of, let's say, plus infinity. Okay, all of these will have plus infinity. So it's the same network that we had used in the algorithm as well. Okay. Great. So, okay, so now let's ask ourselves this question. What is the value of the mean cut in this network? Or what is an upper bound on the value of the mean cut? So I'm not asking you what is the exact value of the mean cut, that needs to be seen. But what is an upper bound on the minimum cut in this network? Like, is it a finite quantity or can it be infinite? Very good. Okay, so the mean cut value is less than or equal to n, right? Why is this less than or equal to n? Well, clearly I have a cut which is of size n. So if I just take this cut, then this has a size of n. So whichever is the minimum cannot have a size of more than n. Yeah, that's very straightforward. Now what we are going to prove is that minimum cut is also greater than equals to n. Okay, so it's, yeah, so if you combine this together, then it will give you that the minimum cut is exactly equal to n. Yeah, so why does this help? So suppose you are able to prove this fact, what does this imply then? Of course we have to see how to prove this, but suppose we are able to prove that the mean cut value in this graph, and remember this has nothing to do with any algorithm or anything, this is an existential fact, that the mean cut in this graph is n. So the point is, now you can apply the max flow equal to mean cut theorem. So that will give you that the max flow in this graph is exactly equal to n. And what does that imply? Well, that will imply that there is a perfect matching in this graph. Okay, so this is the series of implication. But all this will depend on the fact of whether you can prove mean cut is at least 10. So let's see if that is the case. So let's fix any cut in the graph. So fix any estimate. Okay. Okay. So I'm going to prove that the capacity of any cut, any ST cut in this graph is at least n. Okay. Okay. Now note that if I have an edge, so okay, these have some directions. So if your cut happens to be something like this, so suppose your cut, so remember I'm just now arguing about any ST cut in the graph. So suppose your cut looks something like this. You have S and this is your cut. Yeah. If this is the case, then clearly this is true. Right? Why is this true? Because, well, I have an edge that is going out of this cut, which has a capacity of infinite. Yeah. So if you have a cut which looks like this, which has an edge, yeah, it's, yeah, I'm sorry, there is a lag today. So I've drawn it already. I don't know why it's not showing up. Yeah, this is a problem. Okay, there seems to be an issue with the network. Yeah, now it's back, hopefully. Okay, so if I look at such a cut which has an edge between x and y going out of them, so it has these edges, right? These edges going out of the cut. Now these cuts I do not have to worry about. Why don't I worry about these cuts? Well, because these cuts already have a capacity of infinity by my construction. So there is no issue at all with such cuts. So the only cuts that I have to worry about are those such that these blue category of edges, they do not cross this cut. Okay, so fix any cut s. Now if a blue edge crosses the cut, then its capacity is greater than equals to infinity. Yeah. Oh, this is really bad today. I don't know what to do about this. You can see my writing, right? Yeah, I can try that. Okay, just give me a second. No, I don't think it's any better. It's some network issue. Okay. Yeah, now it's even worse. It does not even turn up. Okay, guys, I think we cannot continue today. So there is a serious network issue on my side, probably. So I don't know. Probably I would just record these lectures and upload it. Okay, so you can just take a look offline and maybe we can then discuss if you want. Yeah, I knew you were going to show up at some point, but can you actually see my screen right now? Okay. Hmm. Okay, some people can, but most of you can. So if I write something, can you see this writing? Hmm. Yeah. So I think this is a problem now. Hmm. Okay, so then, yeah, there's no point pushing this because I think there's a network issue today on my side. So this lecture I will just record and upload. Let's try once more on next Tuesday, maybe. And yeah, if this persists, then the rest of the course I will just upload the material. I will just record it offline and upload. Okay. Sorry about this, but yeah, can't help. Okay. Okay, so yeah, so there's a tutorial tomorrow. Those of you who are interested should join in, and yeah, I will upload these lectures offline.
Okay, so right. So remember we were trying to prove Hall's theorem last time, and we could not finish the lecture because of lack of connectivity. Um, so remember what was Hall's theorem? Well, I'm given this bipartite graph, yeah, and I'm asking myself the question that does a perfect matching exist in this graph? Yeah, and we said that there exists a necessary and sufficient condition for the existence of a perfect matching. And what is this condition? Well, the condition is if I look at any subset of vertices on the x side, and if I look at the neighborhood of that set, then the size of this set S is has to be at most the size of the neighborhood set. Yeah. So if there exists a subset S on the x side such that its size is actually greater than the size of its neighborhood, then a perfect matching cannot exist, which is indeed the case in this picture, right? Now, what this theorem is essentially saying is that these are really the only bottlenecks um, in the path of the existence of a perfect matching, right? If such things does not exist in your graph, then you will always find a perfect matching, right? And this is an if and only if statement. So the existence of a perfect matching will imply that this is true, as well as the reverse thing, right? So we saw that one direction is relatively simple. So if I give you a perfect matching, then it's very easy for you to convince me that for any subset S of X, this has to be true. And that's clear because, well, you pick your set S, and since there exists a perfect matching, this set S has to match with some vertices of Y, and the size of this neighborhood set is clearly then equal at least as much as the size of S. Yeah. So note that here I am only showing the edges of the matching, but in the graph there could be, I mean, the neighborhood size could be even larger. Yeah. but at least it should be as large as S. So this side is easy. The other side turns out to be relatively non-trivial. So suppose that I give you this information. So suppose mod of S is less than equal to mod of the neighborhood of S, and this has to be more precise. Suppose this is true for all subset X of S, S of X. Okay. So now how do I convince you that then a perfect matching must exist? And there are several proofs of this fact, starting from induction to using contradiction, using properties of bipartite graph, and so on and so forth. But here I am going to show you proof by a direct application of the max flow equals to mean cut theorem. Yeah? And because I want to apply this theorem, I will construct this flow network. So given my graph x, y, and the edges, now I augment this graph with some other edges and some capacities so that I have this flow network on the graph. Yeah. Please note that I'm not going to apply any algorithm. This is just an existential proof, but I will use this flow network to conclude something about the original graph. Okay. So I hope all of you remember how this flow network typically looks like. So there is an edge from the source S to every vertex on X. There is a edge from every vertex from every vertex in Y to the sink T, and all these edges will have capacity 1, and the capacity of the edges that we derive from the given graph, those will have capacity infinity. Yeah. So think of infinity as a very large number. So it's much larger than the total number of vertices and edges in my graph, suppose. Yeah. So it's not really infinite. It's a symbol just used to say that this is very large. Okay. Great. So suppose I have constructed this flow network. Now what I'm going to convince you is that the size of the mean cut in this graph is exactly equal to n. And why should that be good for me? Well, if I convince you that the size of the mean cut is n, then I will apply the max flow equals mean cut theorem. That will convince you that the max flow in the graph is exactly equal to n. And if the max flow in the graph is exactly equal to n, well then clearly there has to exist a matching which is of size n. In other words, that has to be a perfect matching. Okay, so that's the series of implications that we will use. So the only thing that remains to be shown is that the mean cut is equal to n. Well, the first observation is that the mean cut is at most n. Why is that? Well, because if I take the cut where I have the source S on one side and everything else on the other side, clearly this cut has a size of exactly n, which means that the minimum cut will have size at most n. It cannot be larger. Okay. Now what I'm going to convince you is that the mean cut size is at least n. Yeah. And the two facts together will then imply that the mean cut size is exactly equal to n. Yeah. So this thing which I have boxed out, that is the one which I'm going to convince you about. Okay. So in order to do that, so first of all, let me tell you about this color coding of the edges. So I have colored it so that the picture is pretty clear. So the green edges are the one which go from the source to the X side. The red edges are those which go from the Y side to T, and the blue edges are those which I have derived from my bipartite graph. Yeah. In particular, the blue edges have a capacity of infinity, and both the green and the red category of edges have a capacity of 1 each. Okay. So now I have to convince you that give me any cut, the size of that cut is at least n. Okay. So you give me your favorite cut, I will convince you that its size is at least n. Okay. So suppose you give me this cut. Yeah. Suppose, I don't know, suppose you give me this cut. Yeah. That's a cut in my graph. Now the point is that if you give me this cut, then I will say that I am done readily. I don't have to do anything at all. Why? Well, because there are these blue edges crossing this cut. So even if one blue edge crosses the cut which you gave me, then I can readily conclude that the cut size is at least infinity. Yeah. So I have nothing to prove really for those category of cuts. So this is exactly what I've written here. If a blue edge crosses this cut, then its capacity is at least infinity. So we better not worry about those cuts. Okay. So which are the cuts about which I might worry a little? So which are the cuts for which there is a chance that the cut size might actually drop below n, or at least they have finite capacity? Okay. So if you think about it, those are the those category of cuts are as follows. So basically, let me show you a cut which is of that category. So suppose I give you this cut. Yeah. So that is the A size of the cut, A side of the cut. Yeah. And everything else is on the B side of the cut. Okay. Okay. Good. So now if you observe, there are no edges, there are no blue edges that are crossing from the A side to the B side. Remember, there is an edge, I mean, there might be an edge which crosses from the B side to the A side, but those I'm not concerned about. Yeah, I'm only concerned. So when I claim the capacity of a cut, I mean the capacity of the edges that are going from A towards B, because that defines my flow between S and T, right? After all. So if you think about it, such cut, so this kind of cut, it will, so it does not have any blue edge crossing the cut, right? Okay. So now I cannot say that the capacity of this cut is infinite. It's surely a finite quantity. So let's think about what is the size of this cut, right? So, so suppose now there does not exist a blue edge crossing the cut. Okay. Now, so what are the edges that are really crossing the cut? Well, so the question is, what are the edges that are crossing? Okay. So I claim that there are two categories of edges. Of course, they have to be either green or red because there are no blue edges crossing this cut. Yeah, that's the category of cut that I'm looking at. But how does the green and the blue edge look like? Okay, so let's have some notation. So let capital S be the vertices from X that are on A side of the cut. Okay. So in this picture, what is this set S that I'm talking about? Well, this is the set that I'm talking about. Yeah. So I'm looking at the X side and I'm looking at the vertices that are present inside this cut A. Yeah. Present inside the A side of the cut. So that's my S. Okay. Good. Right. So now, okay. So if I have this notation, then the total capacity of green edges crossing this cut, okay. So what is the total capacity of the green edges? Well, all the vertices which are in capital S are inside this cut. So those green edges do not cross the cut. Everything, all the other green edges cross the cut. Yeah. So in particular, those are the edges that are going from the source S to the vertices in X minus S. Yeah. All the vertices which are in X but not in this set S. Right. Those are the green edges that adds to the capacity of this cut. Yeah. So this is exactly equal to, and remember the capacity of each of these edges is 1. So this is precisely mod of X minus S. Okay. Now, what is the total capacity of the red edges? Capacity of the red edges. Okay. Good. So which are the red edges that are really crossing this cut? So if you think about it for 1 minute, the red edges are precisely those which are going from the neighborhood of capital S to the sink T. Yeah, in this picture, these are the red edges that are crossing the cut. These red edges cannot cross the cut. Why? Because they are already part of B, right? So they are not counted in the capacity of my cut. So let me also show this with some color. So in particular, these are the vertices which are responsible for the red edges crossing the cut. Yeah, but I know that these are precisely this is precisely the neighborhood of this set S that I have defined. Yeah, so the total capacity of the red edges is exactly equal to mod of the neighborhood of S. Okay. So now if I put these two together, then what is the total capacity of the cut? Well, the total capacity of the cut is just the summation of these two quantities, right? So this is equal to x minus s plus mod of neighborhood of s. Okay? But what do I know about my graph? Well, I know that for any subset S of x, the neighborhood set has a size which is at least the size of mod S. Yeah. So I can just replace this with at least. So this remains as it is, but this I have put a greater than equals to. So this I can say to be mod of S. Yeah. So this is using the given condition. Right? So remember, I have assumed that there are no Hall sets in my graph. And now I'm sure all of you are seeing what this summation is. So this is precisely equal to mod of x, which is n. Okay? So that's what I wanted to prove, and I have proved that fact. Yeah? So you give me any cut. To summarize, if you give me any cut in this graph, either there has to be a blue edge crossing this cut. If that's the case, then its capacity is already very large. I don't have to worry about it. If no blue edges crosses that cut, even then I have convinced you that the cut size is at least n. Yeah, just by using this property that there are no Hall sets in my graph. Okay, and this completes the proof. Okay. So in the next video, we are going to explore another application of the mean cut theorem. So hopefully the proof of Hall's theorem is clear.